In 1995, astronomer Robert Williams wanted to point the Hubble Space Telescope at a patch of the sky filled with nothing special, and that too for 100 hours. His colleagues criticized him as they thought it was a terrible idea and a waste of the telescope's precious observing time. But the criticism did not matter because he had 10% of the observing time at his disposal as the Space Telescope Science Institute director. He could do anything with it. Williams said that if nothing exceptional came out of it, he'd resign from the post. So for 100 hours, between December 18th and 28th, Hubble stared at a patch of sky near the Big Dipper's handle that was only about 1/30th as wide as the full moon. The telescope took 342 pictures of the region, each exposed for between 25 and 45 minutes. And it turned out that the seemingly empty region of the sky was full of galaxies. More than 3,000 came spilling out, some roughly 12 billion years old. Galaxies of all types: spirals, ellipticals, lenticulars, red, blue, orange, yellow. The pictures cracked the universe in ways scientists could never have imagined. Today, this composite image is known as Hubble Deep Field. As impressive as the Hubble Deep Field was, astronomers wanted more, and almost 3 decades later, the $10 billion James Webb Space Telescope finally provided that opportunity. Webb's long-awaited first year of science observations, known as Cycle 1, began by mid-2022. 2 of its Cycle 1 programs spent dozens of hours looking for distant galaxies in the early universe by staring at separate small portions of the sky. Astronomers did not expect anything remarkable. They thought they would get a refined version of the Hubble Deep Field from these 2 short-period Cycle 1 programs. Instead, to their surprise, such galaxies sprung into view immediately. Astronomers began spotting galaxies that must have existed in the first 200 million years of the Big Bang. The researchers were excited because Webb suddenly opened the windows to the last significant unexplored era in the history of the universe. However, those galaxies were not like what we had expected. Instead, they were exceptionally bright with a stellar mass of billions of solar masses. Such giant evolved galaxies defy the expectations set by our standard model of the universe's evolution. So where did we go wrong in our models? How can we explain the new extragalactic observations made by the James Webb Space Telescope? Finally, and most importantly, do these observations mean the Big Bang Theory is wrong? To understand the puzzle, let's go back to when the universe was believed to have formed. Within the first second after the Big Bang, all 4 known fundamental forces had separated from each other. The universe was an incredibly hot and dense soup of primordial particles. Over the next 3 minutes, as the cosmos expanded and cooled, the nuclei of helium and other very light elements began to form. Fast forward 400,000 years. The universe was cold enough for the first atoms to appear. The first stars were born about 150 million years later, ending the Dark Ages. These giant stars, called population 3 stars, comprised mainly of hydrogen and helium with no heavier elements like the modern-day stars. They formed the first proto-galaxies, or the clusters of gas that clung to vast, invisible dark matter structures. Thanks to gravity, these proto-galaxies merged to form large galaxies. This complex process is thought to have taken about 1 billion years. But Webb's observations challenge this entire model. Astronomers say that they should be seeing lots of these little proto-galactic fragments that haven't yet merged to make a giant galaxy. In contrast, they are seeing a few things that are already big galaxies. One of them is GLZ 13, having a redshift of 13.1. In astronomy, Redshift is denoted by a dimensionless quantity, z. Z equals 0 denotes present time. And as its value increases for deep space objects, so does its distance and our look-back time. Discovering galaxies above a redshift of 11 is a big deal. And in its 30 years of exploration, Hubble could only find one. However, Webb is an infrared observatory, and it can easily peer at the regions of the cosmos that even Hubble could not. GLZ 13's redshift tells us that it existed in the first 300 million years of the universe. The initial redshift observations were photometric, which means it was determined by studying the galaxy in different colored filters without spectroscopic analysis. Since the photometric redshift isn't too accurate, astronomers thought there might be a problem with the redshift value. But the follow-up observations by the Atacama Large Millimeter Array, or ALMA, in Chile, suggested that's not the case with this candidate. It indeed has a redshift of about 13. In addition, GLZ 13 has a mass of 1 billion solar masses, which contradicts our star formation models. That's because even if you took everything that was available to form stars, you would still not be able to get that big so early. And if star formation was indeed happening so quickly and efficiently, why don't we see it in modern-day galaxies? These observations are difficult to explain with our standard model of cosmology, the lambda CDM model. Here, lambda refers to dark energy, and CDM is cold dark matter. At present, astronomers are desperately trying to fit Webb's observations into the various cosmological models. For example, proponents of the lambda CDM model say that high-mass star formation may be very efficient in the early universe. This is because the temperature and gas pressures are high, which dramatically impacts star formation. Perhaps even magnetic fields arose earlier in the universe than we thought, playing a significant role in driving material to kickstart the birth of stars. Another simple solution is that galaxies in the early universe could have little or no dust, making them appear brighter. The Webb observations may also support the controversial idea of modified Newtonian dynamics, or MOND. Proposed in 1983, MOND says that dark matter does not exist and large-scale fluctuations in gravity can instead explain its effect. There are quite a few observations that can be explained by MOND instead of the lambda CDM model, and Webb's initial observations align with this idea. Although the James Webb Space Telescope has detected dozens of galaxies that do not fit our cosmological models, it doesn't mean that the Big Bang Theory is wrong. That's because it has been developed over the past century with many observational pieces of evidence that one cannot simply ignore. For example, the Big Bang accurately predicts how much of each element was made in the early universe. When astronomers look at very old galaxies and stars, the amount of each chemical element they see agrees with the Big Bang Theory. In addition, the redshift of distant galaxies aligns with the Big Bang model. The light we observe from galaxies has been stretched by the time it reaches us. It looks redder than it should. This redshift is the result of galaxies moving away from us. Observations show that pretty much everything in the universe is moving apart. If you could wind time backwards, you would see galaxies getting closer together. If you could go back far enough, everything in the universe would have been in one place, just as the Big Bang Theory predicts. And perhaps the most convincing evidence is the cosmic microwave background proposed on the grounds of the Big Bang Theory in 1948 and discovered in 1965. The first extragalactic programs of Webb have shown that our models of star formation and galaxy evolution need revisions. The upcoming Cosmos Webb program is expected to hugely increase the population of early galaxies by observing a wider area of sky for hundreds of hours. Astronomers expect to find thousands of such galaxies, refining our database and enabling us to develop accurate models. Some estimates suggest Webb could see as far as a redshift of 26, just 120 million years after the Big Bang. If it turns out to be accurate, it would be a turning point in astronomy. This concludes the 26th episode of the Sunday Discovery series. So if you've enjoyed this video, make sure to like it, subscribe to our channel, and press the bell icon so that you don't miss any future videos of this series.